In this chapter, which is chapter 8, we are going to talk about reactions and synthesis of alkenes, how to prepare them, and some reactions of alkenes, particularly the electrophilic addition reactions. In the previous chapter, we learned about how to add an HX molecule to an alkene, and we also looked at the mechanism of how to add an HCl or an HBr to an alkene, either symmetrical or unsymmetrical. If you recall from the previous chapter, we had an alkene, either a symmetrical or an unsymmetrical. So if you add HBr to it, you get the addition reaction where the Br goes to the more substituted carbon following the Markovnikov's rule. Okay. In addition to that, in addition to this reaction, we have several other reactions which are extremely important, and they can all be made from the starting material, a simple alkene. Some of the reactions can be seen in this summary chart here. You can see that an alkene can be converted to an alcohol, an alkane, a diol, any carbonyl compounds, cyclopropane, epoxides, halides, a 1,2 halide, or a halohydrin. Okay, so a wide number of reactions can be done using alkenes as our starting material. So first, let's look at how to prepare alkenes by two simple reactions. First one is an elimination reaction. Remember in chapter 6 we talked about the types of reactions, and one of them was elimination reaction. So you can actually use this reaction to prepare alkenes. So if you have an alkyl halide and it is treated with a base like potassium hydroxide in ethanol solution, this is ethanol, you can actually do a dehydrohalogenation, which means you are not only removing a halogen but also a water molecule, resulting in the formation of an alkene. Okay, so this is a common method to synthesize alkenes. I'll give you another example. So if you look at, if I have a alkyl halide like this, and if I treat it with potassium hydroxide, which is a base, okay, so you need a base. That's you can use potassium t-butoxide, you can use potassium hydroxide, and then ethanol is the solvent. So we have CH3 CH2OH, which is ethanol. This is the solvent. It is not reacting with the reaction mixture. It is just acting as an inert solvent and resulting in the formation of an alkene, and the side products are KBr and water. Okay, so this is another example of dehydrohalogenation, which is a good method of synthesis of alkenes. Another method which is usually done is the dehydration reaction, and it is usually done in the laboratory by treatment of an alcohol with a strong acid like sulfuric acid. It is also heated to a temperature of about 50 degrees Celsius, and this is done usually in a solvent like THF, tetrahydrofuran. This results in the loss of a water molecule and formation of an alkene. Okay, so here again I can give you a similar example so that it helps you to remember. We'll put OH here and then do the same thing. We have the reagents on top of the arrow. Here it is sulfuric acid, and then we are heating it to 50 degrees Celsius in THF. Remember, the this THF is a solvent. It is not going to react with the it is not going to react with the reactant here. Okay, so you get an alkene and then you get the side product as H3O plus. Okay, so this is another good method of preparation of H2O. Okay, good method of preparation of alkenes. These both methods are given in your textbook, so please review those. Now let's look at the reaction. So as I was showing you, this chart here summarizes the most important reactions which we will be looking into this in this chapter. This video we will cover two of them. One is how to form alcohol from alkene, how to form dihalides from alkene, and maybe we can do one more, and that is how to form the acid halides from alkenes. This reaction we have already looked at in chapter 6 and 7. You know the mechanism of this, but we can go through it one more time, and we will do a couple of other reactions along with that. That is the formation of the dihalide, formation of halohydrin, and alcohol. Okay, so in this video we will cover these four reactions. So first let's start with hydrohalogenation, which we have looked at in chapter 7, where you take a alkene. So we are looking at reactions of alkenes now, reactions of alkenes. And the first reaction we are looking is called as hydrohalogenation. That means you take an alkene, and I'm going to use an unsymmetrical alkene because it helps me to talk about Markovnikov's rule. So I have an unsymmetrical alkene and I treat it with the hydrohalide like HCl or HBr to form an alkyl halide, an addition reaction. Okay, so your hydrogen gets added to one end and the Br gets added to the other end. Now how does the mechanism, how can we write the mechanism of this? If you recall again, the pi electrons on the double bond, they are electron rich. The pi bond is electron rich, so that acts as the nucleophile. So this is my nucleophile, and these are all called as electrophilic addition reactions. So you can see that this nucleophile attacks the electrophile. That's because the Br is more electronegative, pulls the electron towards itself, making the hydrogen more the positive end. So the nucleophile attacks this. We can label this as electrophile E. So the intermediate that is formed is the carbocation. Now remember, we talked about the carbocation can be formed here or here, but this is the preferred site because the more substituted carbocation is more stable. Okay, so this is a tertiary, a secondary carbocation. Okay, this is a secondary carbocation, and Br minus is kicked out in the first step. In the next step, we have the Br which is acting as my nucleophile. It goes and attacks at this carbon atom, which is my carbocation, and gives the product here. Okay, I have not shown the position of the hydrogen, but if you want, we can put a different color so that you can track the where the hydrogen is going. So I'm putting a red color for this hydrogen, and that is the hydrogen that is attached here. Okay, let me just use the black color for the bond. Okay, all right, so we have a hydrogen attached here, and then we can again keep showing the hydrogen on this side and here. And that's how my final product is formed. Okay, so this is my product, and this is the mechanism of the formation of the alkyl halide. Now, if you had a chiral starting material, if your carbon atom is a chiral compound, then what can happen is you can get a racemic product. That means the Br minus can attack from the top or from the bottom with equal probability, and you might get a racemic mixture. Okay, so if you have a chiral starting material, then you end up in a racemic product. That means you will get equal amounts of R and equal amount of S enantiomer in your final product. Okay. Let me show that to you as an example. Okay, so we have another example. This is the product, correct? Because this will be where the chloride will be attached. Now if you look at this carbon atom is a chiral center, right? So if you write the mechanism of this, it will be where the first step is attack of the double bond onto the electrophile, nucleophile electrophilic attack to form the carbocation. Here is where the carbocation is formed, and you have the Cl minus. Now this is where I was talking that the chloride can attack from the top or from the bottom with equal probability, right? So this results in the formation of the equal amounts of the two enantiomers. You can have a chloride pointing out or a chloride pointing at the back. Okay, so stereo specificity of this reaction is that you will get equal amounts of R and S product. That means you get a racemic product. Okay, so for all these reactions, stereochemistry and regioselectivity are important. This is a regiospecific reaction. Again, why regiospecific? Because one region is preferred over the other. See, the carbocation was formed over here rather than here because a secondary carbocation is more stable than a primary carbocation. Okay, so these reactions are regiospecific, and stereospecificity is that it produces a racemic mixture, right? Okay, let's look at the next reaction. Oh, one more important thing I would like to add is in case you have a rearrangement of carbocation, then how will the products be affected? Okay, so for example, I will take an alkene of this kind. So we have this double bond here, and I have a substituent here. Okay, and I do the same reaction, react it with HCl. What will be the product? So actually here we will get two products. One where the Cl has been attached here. Okay, that's the expected. But then we also get another one where the Cl is attached here. So actually this will be my major product, and this will be my minor product. Okay, and the reason, let's look at the mechanism to understand the reason for the formation of these two kinds of products. So first is that we have the formation of the carbocation. So same mechanism where the nucleophile attacks the electrophile, chloride is kicked out, and you get this carbocation, correct? The hydrogen is attached to this carbon atom. However, now this carbocation can actually undergo rearrangement. Why? Because there is a more stable position here. So one of the hydrogen atom here can shift over here. So we call this as a hydride shift to give the more stable carbocation, which is your tertiary carbocation. Okay, so the hydrogen here, which was in the tertiary position, let me put it like this. Okay, so the hydrogen here moves over to here, right, and gives room to the more stable carbocation, which is your tertiary carbocation, and that's why this becomes your major intermediate. So tertiary, and this is secondary, so this is more stable. So now the Cl minus is going to attack on this position and give you this product. Okay, if the Cl minus attacks this position, then it gives this product. But since tertiary carbocations are more stable than secondary, this will become my major product. Okay, so hydride shifts are important. And so hydride shifts whenever possible to give a more stable carbocation. Okay, all right. Now let's look at the next reaction, which is HBr addition with peroxides. Now in this case, it follows an anti-Markovnikov's rule. So in the previous one, we had the Br attached to the more substituted carbon, but if you want the Br to be attached to the less substituted carbon, we use these conditions where we do it in the presence of a peroxide, and H nu here stands for light. So in presence of light, this is a free radical mechanism, and you can get the product where the Br is attached to the less substituted carbon. Okay, so the mechanism is like this, where remember in chapter 6 we talked about free radical mechanism. So this peroxide gives you peroxide radicals, and these radicals then give you a source of Br radical, and then the Br radical is then this has a homolytic cleavage of the pi bond, and you form the product in this manner. Okay, so this mechanism I'm not going to ask you, it is just for your information. However, you should be able to write down the product in case I give you the conditions, and be able to say that Br is attached to the less substituted end. Okay, another reaction we are going to look into is the addition of halogens to alkenes. the halogens like bromine and chlorine, they will add on to alkenes to give the 1,2-dihalides, like a 1,2-dichloride or a 1,2-dibromide. Fluorine is too reactive and iodine does not add, so we don't have to worry about these two reagents. However, we'll look at reactions involving bromine and chlorine. Okay, so this is a simple illustration where you take an alkene, react it with chlorine, and you can see that the chlorine gets attached to the double bond, or opens up the double bond, and it attaches itself to the two carbon atoms. This is the starting material for our formation of vinyl chloride, and vinyl chloride is the monomer for polyvinyl chloride, which is a very useful polymer. Let's look at the mechanism of this. It has been seen that when bromine or chlorine adds on to a double bond, then the product is exclusively trans. That means the the halogen molecules, halogen atoms, they are attached trans to each other always. We never get the cis product. Okay, so to illustrate that in a little different manner, so if you have an alkene, okay, and then you react it with Br2, then what will happen is you get a trans addition where one Br is down and the other Br is up. You will not get the cis product where both Brs are either down or both Brs are up. Okay, so this is my exclusive product. That means it's a stereo-specific reaction where the anti, we call this as the anti-addition, is what is seen in this type of reaction. Okay, so the mechanism that has been proposed is that it's not a carbocation mechanism, but here the bromine forms a tri-membered ring with the two carbon atoms to form a bromonium ion. Okay, so it forms a cyclic ion like this one. And how it is done is, again, the nucleophilic attack on a bromine. So the Br gets, one of the Br takes up the electrons pair, making this delta positive. So the nucleophile electrophile attack happens and it forms a bromonium ion intermediate of this kind. Once this is formed, now the next Br atom, or the Br that was kicked out in the first place, this one, is going to do a backside attack, right? Because it cannot attack from the other side because it's blocked by this ring, right? So it goes from the back, pushes these electrons over here. So that's why we end up in a trans product. Okay, so this can be better illustrated by this cyclic ring example. If you look, the one of the Br species blocks the one side of the ring, so the other Br has to attack from the top side, as a result of which you get the trans product. Okay, you can do this reaction with chlorine also, and it will be called as a chloronium ion intermediate. This was actually it was actually proved that this bromonium ion intermediate is formed because the scientist George Olah was able to isolate stable solution of this cyclic bromonium ion. So which is a proof that yes, this is the kind of mechanism that we have to follow for the addition of Br2 to an alkene, or an Cl2 to an alkene. Okay, all right. Next reaction which we are going to look at is addition of halogen and water simultaneously. So it's called as a halohydrin formation. This product is called as a halohydrin. So the mechanism is kind of similar to what we saw before, the first step at least, that the halogen forms a tri-membered ring, and then the water molecule is the nucleophile and it attacks from the backside. Okay, so here if you look, the first step is the formation of this tri-membered ring. Just like we saw in the halogenation, a bromonium ion intermediate is formed, but in the next step, water is acting as my nucleophile. Okay, rather than Br minus, water is acting as a nucleophile. It goes and attacks from the backside, pushes this Br up, and then we get a trans product again. Okay, this results in the formation of a halohydrin, where we have one of the carbon atoms having the Br and the other carbon atoms getting the OH. Okay. Now, if you have an unsymmetrical alkene, like an unsymmetrical alkene like this, then it is important that you understand that the OH group, which is from the water molecule, that goes to the more substituted carbon always, and the Br goes to the less substituted one. Okay, so Br and OH are always trans. So there are two things you have to consider in this reaction, that the stereochemistry is anti. That means the Br and OH which are added, they are anti to each other. At the same time, you have to also take into consideration that the OH, which is the coming from the water molecule, is always attached to that carbon atom which is more substituted. Okay, so keep in mind when you write down the products that OH is attached to the more substituted carbon, and OH and Br are always attached and tied to each other. Okay, the stereochemistry. Instead of bromine, you can also use this source which is called as NBS, N-bromosuccinimide. This is a slow source of bromine and also a safer source of bromine to use, but you end up in the same kind of product where you get a Br and an OH. Okay, so here again your nucleophile in the second step is water, and you end up with the OH going to the more substituted carbon. See, this carbon has a phenyl group and a hydrogen, so this is my more substituted carbon, so OH has to be attached to the more substituted carbon. The third type of reaction which we can look into is the hydration. Hydration of an alkene, that means adding water to double bonds. But this has to take place in presence of a catalyst like a strong acid like H2SO4 or H3PO4. It doesn't matter which acid you use. It is a strong acid and formation of alcohol. So alkenes can be converted to alcohol. Now here actually the formation of alcohol from alkenes, we will do it in three different steps, okay, or in three different reactions. We'll look into three different reactions. One is just now we looked at that hydration of alkenes in presence of acid catalyst. Second is oxymercuration. They all result in the formation of alcohols. Okay, so here the three types of reaction to convert alkenes to alcohols is what we are looking at. One is you can do hydration of alkenes in presence of acid catalyst. Other is oxymercuration followed by demercuration or followed by reduction. And then third is hydroboration followed by oxidation. Hydroboration followed by oxidation. So there are three methods which we will look into in this formation of alcohols. First one is the hydration of an alkene in presence of an acid. So how does the mechanism, how can we explain the mechanism of it? What is the role of the acid? So the acid here, this acid is represented as H3O plus, is there to so the nucleophile attacks this hydrogen forming a carbocation. Water is acting as a nucleophile, goes and attaches itself as a whole to the carbocation, to the carbon which has the positive charge. Another water molecule acts as a base, pulls off the hydrogen and forms the alcohol. Okay, so we can do this one more time. Let me take an unsymmetrical alkene in this case. Okay, so I have an alkene reacting with H3O plus. Now where did this H3O plus come from? That is from the acid. Remember we did this in the acid catalyzed hydration. This is called as acid catalyzed hydration. So the H3O plus is from the acid. So we have a nucleophile electrophilic attack, putting these electrons over here. So the first step is formation of the carbocation. Water is formed, right? The next step, the water attacks the carbon atom with the positive charge. So nucleophilic electrophilic attack. You result in a formation of this molecule or a species, but oxygen has to get positive charge because it is 3 bonded, right? So this oxygen goes and attaches itself here. Now in the next step, another water molecule now acts as a base, pulls off this proton, puts this electron back over here to give you the product which is your alcohol. Okay, so you converted an alkene to an alcohol, and the mechanism is like this. Here again, since we are forming a carbocation, you have to make sure that the carbocation is formed on the more substituted carbon. Okay, so what if I had given you something like this? Okay, again, remember we talked about carbocation rearrangement. Oh, sorry. So if I have an alkene like this, and I do the same reaction, presence of H2SO4, what happens if I react it with sulfuric acid? You will say that the formation of an alcohol, but where will the OH be? This will be my major product. Okay, so if you recall, we will do a similar mechanism, okay, where you have your alkene attack the electrophile. Here again, the H3O plus is from the acid. So you attack here, put the electrons over here. Now you get a positive charge carbocation formed here. But remember, we have a rearrangement happening, right? Because there is a more stable carbocation. So it rearranges itself to the positive charge here, right? And then water molecule now attacks at this point to give you the OH2 with a positive charge on oxygen. Another water molecule grabs the proton, puts the electron back, and then results in the formation of this product. Okay, so you have to watch out for carbocation rearrangement whenever your mechanism involves a carbocation. Right? So these are two examples, one where it is showing that the carbocation is formed in a secondary position. Here there is a rearrangement where the secondary carbocation rearranges itself to give this tertiary carbocation because it's more stable. Okay. All right, now we move on to the next type of hydration reaction, where we are doing in presence of a mercuric acetate. Okay, using mercuric acetate. Now in this case, there is no carbocation. Here the mercuric acetate forms a three-membered ring like this. The water molecule attacks from the backside, and then the final step is where you use a sodium borohydride to like a reduction reaction where the HGOAC is replaced by a hydrogen. Okay. If you look at this reaction, again, Markovnikov's rule is followed where the OH goes and attaches itself to the more substituted carbon atom. So we have an unsymmetrical alkene. So OH attaches itself to the more substituted carbon atom. However, this is not a carbocation mechanism. It involves a mercurinium ion, so you don't have to worry about carbocation rearrangements. So this type of reaction is actually used in lab scale, laboratory scale reactions because we really do not want too much rearrangements, or otherwise we will end up in a lower yield of the product. So in labs, we try to use this mercuric acetate when we have to make the alcohol in smaller quantities. Okay. All right. So once again, the reaction forms a mercurinium ion where the just like bromonium ion we talked about, right? So mercurinium ion is formed from the mercuric acetate, mercurinium ion, and then the water molecule now acts as a nucleophile. It attacks from the backside because the front side is blocked with this three-membered ring. So water attacks from the backside. This opens up. So we have OH here and the HGOAC, which then in the next step a demercuration happens, and the mercury is replaced by a hydrogen here. Okay, so I'm not going to look at the detailed mechanism of this. It's a little complex. Actually, I have it on the next sheet, but I'm not expecting you to write this down. Okay, as long as you know that the intermediate is a mercurinium ion and not a carbocation, that's fine. Okay, again, here is an example. You have a molecule here, and if I give you this reagents and ask you what the product is, make sure that you have the OH attached to the more substituted carbon. Okay, so these are the two carbon atoms here. This is the more substituted carbon. This is the less substituted carbon. OH attaches itself to the more substituted. Okay, now again, remember THF is just our solvent, so don't worry about having that incorporated into the reaction. It is just acting as an inert solvent. This is the reagent, and we have the second step of reduction where the HGOAC is replaced by a hydrogen. Okay. All right. Now the final reaction is the hydroboration, where we take an alkene and treat it with borane in presence of THF. Again, THF is the solvent, and then followed by oxidation with hydrogen peroxide. So borane is a very reactive Lewis acid because boron has only its octet is not complete, so it can accept electrons. So THF complexes with BH3 to form a BH3 THF complex, and when an alkene reacts with that BH3, what happens is that you get an intermediate of this type where it adds as BH2 and hydrogen. Okay, BH2 and hydrogen, and then it's followed by an oxidation which forms this alcohol. Okay. However, what is the characteristic of this? If you look at, this is a more substituted carbon, right? We have an R group here. Sorry, this is the more substituted carbon. You can see there are two R groups and this is only one R group. But where did the OH end up? The OH ends up in the less substituted carbon. This is unlike the Markovnikov's rule that we have seen. So this is an anti-Markovnikov or a non-Markovnikov, where the OH attaches itself to the carbon atom which is less substituted. So this reaction is particularly useful when we want to have the OH group attached to the carbon atom which is less substituted. So you use a BH3 THF followed by H2O2 in presence of a base, and that ends up in the formation of this product. Okay. So why this happens is the mechanism where you can look, the BH3 forms a transition complex or a transition state. If you look at, we have a transition state where the BH2 is attached to the carbon atom which is less substituted, okay, because otherwise there will be too much steric crowding. There will be crowding here, so this one is not formed. So where the BH2 goes here, that is not formed. On the other hand, the BH2 goes to this carbon atom which is less substituted, and then when the BH2 gets replaced or it gets the oxidation happens, then the OH ends up in this carbon atom which is less substituted. Okay. So the stereochemistry is important here. It occurs unlike the other alkene addition reactions we have seen because the CH and the CB bonds are formed at the same time. Okay, the CH and the CB bond are formed at the same time, but so the boron will try to look for a position which is less crowded, and that is why we get the non-Markovnikov's addition. Okay, so non-Markovnikov's addition, which again means that we are adding the OH to the less substituted carbon. Okay, so say for example I take a simple alkene like this and do the reaction BH3 THF. THF again, remember, is a solvent, followed by H2O2 and OH minus. This is two steps. Okay, first you do the hydroboration and then you oxidize it with peroxide. So the final product of this would be the OH will be attached here, right? Not on this side because of the way the mechanism is. Okay, the transition state, you can see the boron goes to that carbon atom which is less crowded and avoids steric crowding. So this is not formed. This is the pathway we will take, which results in the formation of OH attached to the less substituted carbon atom. Okay, so this is a summary of the two previous reactions we said. So same starting material, but two different reagents, you see, you get two different products. If you take this conditions, BH3 THF H2O2 OH minus, which is the hydroboration, right? If you take the hydroboration condition, you will have the OH attached to the less substituted carbon. If you take the same starting material but change the conditions, you do the oxymercuration and followed by demercuration, you can see that the OH goes to the more substituted carbon atom. So depending upon what product you want, you can change the reagents, right? So we have looked at a few reactions in this video. We will continue with a few more reactions in the next video.